So in this lesson, we're in lesson 2 of the Modern Biology course in the Classical Liberal Arts Academy, but this is our 4th class. So this is class number 4, but we're on lesson number 2. All right, so let's get our notes ready. Get your name and date at the top of your paper. The name of this course is Modern Biology. Modern Biology, and this is, we'll call it Lesson 2, Part 2. Lesson 2, Part 2. And the title of this lesson is Introductory Experiments in Chemistry and Physics. Introductory Experiments in Chemistry and Physics. But this is not chemistry or physics class, this is biology class. The reason why we're studying or talking about chemistry and physics is because I said that the three high school sciences are biology, chemistry, and physics. Biology, chemistry, and physics. And I said that different schools teach these in different orders. And it doesn't really matter because each of them helps us study the others. In this course, though, we're studying biology, which is the science of life, the science of living things. But we need a little bit of chemistry and physics knowledge to help us in the study of biology. So in this one lesson, in lesson 2, we go through some introductory experiments in chemistry and physics that just provide us with some simple knowledge of chemistry and physics that will help us as we get started in the study of biology. Okay, so some introductory experiments, some introductory observations, introductory information from chemistry and physics that will help us to get going in our study of biology. I'm going to switch over to the textbook now. So we learned that first of all, that natural science, when we talk about natural science is the study of matter. And I've emphasized that again and again and again because this is an error in many modern schools. Modern science is allowed in these schools to give opinions and make judgments on issues that have nothing to do with matter, and that is not appropriate for natural sciences. The natural sciences are the study of matter by means of the senses. Science cannot tell us anything about religion. Science cannot teach us about the origin of the world. Science cannot tell us whether or not we have a soul, whether angels or demons exist, whether God exists. None of those things are the scientist's business. And yet we'll find that scientists very commonly talk about all these things. And they mislead people by making them think that science has proven that this or that is true or false, when it's impossible for science to say anything about many of these topics. Science is the study of matter, of the material world. And we learned that the three basic sciences are biology, physics, and chemistry, as I said before. Physics and chemistry differ from biology. How are physics and chemistry different from biology? How do they differ? Anybody know? How do physics and chemistry differ from biology? What's different? Biology is the study of living matter. Physics and chemistry are the study of non-living matter. Okay? Biology is the study of living matter. Physics and chemistry are, for the most part, the study of non-living or inorganic matter. We talked about compounds and elements in chemistry. We said an element in chemistry, a chemical element, is the smallest possible building block. I shouldn't say smallest, the simplest possible building block in nature. And chemical elements are combined to form chemical compounds. And we named a small number of chemical elements. We talked about oxygen, carbon, nitrogen, and we could go on. These include metals, for example, gold, silver, iron, lead, and others. Those are all elements. Gases, hydrogen, nitrogen, oxygen are elements. If you go online and search for the periodic table, if you Google periodic table, and again, this is not chemistry class, so we're not going to get into all this, but if you just Google periodic table, you'll see that there's a chart that chemists use that shows all of the known elements, all of the chemical elements that chemists have been able to identify. All right, so the periodic table, if you're interested to see how many there are, the numbers change. Some of them aren't even real. They're artificial, and there's questions about that. But if you're interested to know how many chemical elements there are, you can look at a periodic table. In our last lesson, we focused on the first element that we're going to study, and we're looking at a couple of elements. These aren't just randomly selected elements. We're looking at a couple of elements that are helpful in biology. All right? So for example, since we're studying living things in biology, oxygen is obviously important. So if we know some basic things about oxygen, that's useful information. We learned about oxygen. We learned that oxygen is colorless, odorless, tasteless. There's basically no way for us to perceive oxygen. And so the question that I asked was, how can we know it even exists if you can't see it, can't taste it, can't smell it, can't feel it, can't hear it? How do we even know it exists? Do you remember how we know? How?
Like, one of them is if you stick a thing that covers a little fire, then it would just go out.
Even simpler than that. Even simpler. How do we identify oxygen?
Because you can see its effect.
Right, we can see its effects. That's right. We can see its effects. So even though it's invisible, we can see its effects. And you know what's funny about this is that the scientists will say that angels don't exist because we can't see them, taste them, feel, and yet we can see their effects, but they won't accept that. At least some won't. And yet when we ask them how can they prove that oxygen exists, they'll say, well, we look at its effects. Well, that's the same thing we do with God in theology and philosophy, right? But they'll say God doesn't exist because we can't observe him, but we can observe his effects. We can't observe oxygen either. We observe its effects. Okay, so this is an example where they contradict themselves. We're studying something that's invisible, that's impossible to perceive. And yet scientists can understand that it exists and it can be proven to exist by its effects, which is exactly what we would argue about spiritual things. We can see their effects. But anyway, we looked at oxygen. We talked about the properties of oxygen. We said oxygen can be observed by its effects. Still, there's lots to think about there, right? How do we know it's actually oxygen? How do we know it's not just air? You know, you see how there's other questions that arise? Like, just because you can show me that something's burning, how do you prove that it's burning because oxygen is there? All right, so these are questions you should be thinking about. How do these experiments actually prove what the scientists say they prove? Don't just stupidly, lazily accept information. All right, we talked about oxidation. We had a definition for oxidation. The chemical union of oxygen with any other substance is called oxidation. And we said oxidation has a number of different forms, right? What's one form of oxidation? What's one form of oxidation we talked about?
Iron forms rust.
Rust. Okay, good. Rust is one. What's another form of oxidation?
I think fire.
Something burning, right? Okay, so burning is one form of oxidation. Rusting is one form of oxidation. What's another one? Rusting is one. Burning is one. What's another
Water.
form of oxidation? No, not water. But what's another form of oxidation? Decomposing things, right? So decomposing wood, decomposing plants. Oxidation is taking place when things decompose. So when we see fires burning, when we see metal rusting, when we see physical living things decomposing, or not living things, but dead things decomposing, what we're seeing is oxidation. At least that's how chemists explain it, right? I don't want to assert things like, that's oxidation. Like, no, that's what chemists explain oxidation to be, all right? So we talked about oxidation and what that is. Then we looked at a couple different examples of oxidation, and we said one important principle of chemistry is that heat is given off by oxidation, right? We said that's an important chemical principle, is that heat is released when oxidation takes place. So if we want to create heat, what do we need to do? We need to create oxidation. If we cause oxidation, we produce heat. Okay? The second chemical element we're going to look at is carbon. So in this lesson we're going to focus on carbon. Carbon. Where have you ever heard the word carbon before? Carbon.
Car's exhaust.
Carbon, yeah, carbon monoxide, that's called. Okay? The exhaust of a car is called, the gas that comes from the car's exhaust pipe is called carbon monoxide. Where else have you heard the term carbon before?
In the air.
In the air, carbon dioxide. Okay? Another gas, carbon dioxide is another gas. So we've heard of carbon monoxide, carbon dioxide. Any other place you've heard the word carbon?
Carbon wood.
Carbon in wood, right? That's what we're going to talk about, the element carbon. There's a material that's used in modern cars and things like that called carbon fiber. Have you ever heard of carbon fiber? Okay, so it's a material used in modern manufacturing. It's a replacement of metal. They actually make a material that's made out of carbon that's stronger than metal and as light as plastic. Carbon fiber. Okay, so we see this word carbon, right? Carbonated water. You see carbonated water? What in the world? Carbonated water. And so we see this word carbon all over the place. So let's take a look at what carbon is. Let's read what our textbook teaches us about this chemical element. It's an element, carbon. An element. It's a building block of nature, according to chemistry. We read, another chemical element of much importance to us is carbon. This element makes up an important part of all things that now have or at any time had life. That's for your notes. Carbon, write this down. Carbon is present. Carbon is present in all things that now have life or that had life. Carbon is present in anything that is living or has lived. And if you want to hear something interesting that our textbook teaches us, if you want to look in the natural world and find pure carbon, where is it found? It's found in a diamond. A diamond is basically pure carbon. What do you know about diamonds? Do you know anything about diamonds? Have you ever learned any properties of a diamond? I mean, you know they're valuable, right? They're expensive. They're one of the strongest materials in the world. Diamonds are actually used to cut things. You can take a tiny piece of diamond, and they use diamonds to cut glass and cut other materials. Diamonds are one of the, I don't know if they're the strongest material or one of the strongest materials. Diamonds. All organic matter contains carbon. All organic matter contains carbon. Carbon is found making up part of the bodies of plants and animals. Plants and animals. Of coal and in a nearly pure state in the diamond. The presence of carbon can often be detected. So how do we know that carbon is present in something? The presence of carbon can often be detected by the fact that the substance containing carbon turns black when heated by a flame. So if you have ever put something into a flame and it turned black, the reason why it turned black was because carbon is present in that substance.
Put glass in the fire and turn black.
Because there's carbon burning probably from the wood. You see what I mean? Yeah, soot is carbon. So if you put something and the black appears on it, that black is coming from the carbon in the wood, right? What?
Plastic.
Yeah, anything. Well, no, anything. If it burns, it has carbon. I mean, if it burns and produces that black sooty substance, that's carbon. Coal is carbon. And diamonds are actually produced by compressing coal. Diamonds are actually made of coal. When coal is compressed, it forms diamonds. All right, so the presence of carbon can often be detected by the fact that substance containing carbon turns black when being heated. Now, you may not, if you get a fire going really, really hot, you may not see any black. That's not what this is saying. Because then all of the carbon the fire is so strong and the draft of the fire is so strong that it actually blows all the carbon away. But if you heat something, this sounds funny, but if you heat something at a cool temperature for fire, it'll just get filthy and black. Okay, when something is heated, it turns black. But if you get a really, really hot fire going, you won't see it'll just disappear. Okay? So that's one way to sense the presence of carbon, the black soot that remains from fire. So here's an experiment that we're taught in this chapter, because remember, we learned that all scientific knowledge in the natural sciences should come through experimentation, right? Should come through observation. It shouldn't be book learning. So here's an experiment you can perform. Heat on a tin plate, so take a metal plate, and heat some leaves and some sticks, some gravel, some sand, and some topsoil. So mix those things up and put them on a plate. and burn them. Leaves, sticks, gravel, sand, and some rich black topsoil. Place them over a hot flame for a few minutes. Which of the above materials contains carbon? How can you tell which materials contain carbon? Which ones burn black, right? So the sand likely won't burn. The stones won't burn. Organic material. We just learned that. Organic material contains carbon. Okay? If some substance that contains carbon is burned in a jar with a tight cover, the flame will be seen to go out after a short time. This will occur before all the wood is consumed. Why would the flame go out in a jar? Because there's no oxygen left. The oxygen is consumed, and as soon as there's no more oxygen, the fire can't burn. There can be no more oxidation because there's no more oxygen, and the fire will go out. Another splinter of wood placed in a jar with the cover off will burn slowly and completely. A small splinter of wood. A third piece of wood burned in a jar will be quickly and completely consumed. Oh, I'm sorry, not in the jar, in the air. A third piece of wood burned in the air will be quickly consumed. If a little lime water is poured into the jar, which was closed, the contents shaken up, the lime water will be found to turn a milky color. The milky appearance is due to the formation within the jar of a material known as calcium carbonate. Calcium carbonate. So what happens is if you put some lime water in the jar with that burned up wood, it'll form a milky substance that's called calcium carbonate because the lime water and the carbon will unite chemically and form a compound substance. The milky appearance is due to the formation within the jar of a material known as calcium carbonate. This is thrown down in the liquid as a result of the union of carbon with lime. Some of the carbon from the wood has passed in the form of a gas into the lime water and there united with the calcium in the lime. Calcium is another element. Remembering what we know about oxidation, we see that the carbon of the wood has passed off and united with oxygen of the air in the jar. Thus, by the uniting of two chemical elements, a chemical compound has been formed. The presence of carbon dioxide is known by the fact that it puts out a flame. So carbon dioxide does not burn. The presence of carbon dioxide, that's the gas that comes out of our mouth. Carbon dioxide. All right? The gas that comes out of a car's exhaust is carbon monoxide. That's poisonous. Carbon monoxide. Carbon dioxide is the gas that we breathe out. We breathe in air with oxygen. Our body takes the oxygen out of the air in our lungs. That's how oxygen gets into our blood. Our body separates the oxygen, and then we breathe out carbon dioxide. We breathe in the air with oxygen, take the oxygen out, and we breathe out carbon dioxide. The presence of carbon dioxide is known by the fact that it puts out a flame and that it turns lime water milky. This compound is known as carbon dioxide, which we just said. Okay, so carbon dioxide. So what's important to know about carbon? Not these names here. What's important to know about carbon, make sure you have this in your notes. Carbon is a chemical element. Carbon is a chemical element. If you look on the periodic table, on that the chart that I was telling you about before, an abbreviation for every element. The abbreviation for carbon is just a C. It's one of the most basic chemical elements. It is present in all organic things. And by organic, we mean anything that lives or did live. Make sure you're taking notes. Carbon is a chemical element. It is in all organic things. We learned that it joins with oxygen to form carbon dioxide. Joins with oxygen to form carbon dioxide. We also learned that the presence of carbon can be detected by the black soot. Produced by fire, produced by burning, produced when organic things are burned. So carbon is present in the black soot that is produced when organic things burn. So oxygen we learned about is a gas. Carbon is normally present in the form as a solid in the bodies of organic things. And by organic things, I mean things that are living, plants and animals that are living, or dead plants and animals that are decaying. Carbon makes up an important part of all organic bodies. Carbon. Next, we're going to study nitrogen. The next chemical element is nitrogen. Where have you heard about nitrogen? Or
Racing cars.
What?
Racing cars.
Race cars, okay?
Yeah.
What does it have to do with race cars? Somehow mixed with fuel, right? Okay? We have something like nitrous oxide. I think it's spelled O-U-S. Nitrous oxide. Okay? Nitrogen gas. On the farm, nitrogen fertilizer. If you want to fertilize your plants, and you go to the hardware store and you look at the fertilizer, there's 3 substances in fertilizers: nitrogen, potassium, and phosphorus. So nitrogen obviously has something to do with fertilizing plants. Okay, so let's learn about nitrogen in our lesson here. There is another gaseous substance that will not support combustion. Will not support combustion. So you should be thinking to yourself, why in the world would we use nitrogen in a fuel in a car if it doesn't support combustion? That doesn't make much sense, right? So we have to understand how that works. This is the element nitrogen. The chemical symbol for nitrogen is just N. Its presence in the atmosphere can be shown with the following experiment. So here's an experiment how you can identify nitrogen in the air. Nitrogen makes up a large portion of the air. Take a bell-shaped jar and invert it in a large, deep dish of water. having previously placed within the jar on the surface of the water a piece of phosphorus supported on a flat bit of wood or cork. Leave the experiment for 2 days undisturbed. After that time, the water will be found to have risen into the jar. If you make a mark on the cover to show where the water stood, you can measure the space occupied by the water in the jar. This space will be found to be almost 1/5 of the cubic contents of the jar. It was occupied by oxygen in the air, this having been used up by the oxidation of the phosphorus. The remaining space at the completion of the experiment is occupied by nitrogen in the jar, which makes the remaining 4/5 of the atmosphere. So the idea there is that if you take a bowl or a dish of water and you take a bell-shaped jar and put the bell-shaped jar down into the water like this so that there's air trapped in the jar, and it says to put a piece of phosphorus inside the jar that's supported on a piece of cork, what will happen is the phosphorus will react with the oxygen that's in the air inside the jar and will consume that oxygen. And when it consumes that oxygen, the place that was taken up by the oxygen will be replaced with water, so water will start to fill up into this. Water will start to move up into this jar because the oxygen is being consumed by the oxidation of the phosphorus. And 4/5 of the air that was originally in the jar will be left. And that air, that gas that's left in the jar is nitrogen. So you could actually separate nitrogen from the air with this experiment. And there's an illustration in the book that shows how you could set this up. So if any of you want to geek out and try some of these experiments, these aren't very dangerous, so you can try to prepare and conduct one of these experiments or all of these experiments. You could have a jar full of nitrogen that you can play with. I don't know what you'd do with it, but you'd have nitrogen. You could sell it. Go online, sell a jar of nitrogen to somebody who wants to buy nitrogen. I don't know. All right, so what do we know about nitrogen? The physical properties of nitrogen are pretty exciting. It has no color. It has no taste and no smell. It's just like what? Just like oxygen, right? No color. It's invisible. It's all around us here. 4/5 of the air in this room is nitrogen. Has no color, no taste, no odor. Its chief chemical characteristics are the inability to support combustion and its slight affinity to other substances. Okay, so what can we know about nitrogen? Let's get these examples out of here. What can we know about nitrogen? First, it is colorless, tasteless, and odorless, just like oxygen. How is it different from oxygen? How is nitrogen different from oxygen?
It isn't consumed by oxidation.
Right, okay, it's non-combustible. And you know what combustion is? Combustion means to burn. Okay? Non-combustible. So if you light a match, if oxygen is flammable, right? Oxygen is flammable. If you light a match, why doesn't the whole atmosphere just blow up? Because there's other gases mixed in that control how flammable the air is. That's pretty crazy if you think about it. So God created the world, and the gases in the air allow things to burn, but only so much, so that it's safe. If our atmosphere was just filled with oxygen, it would blow up. If you ever see a person who is usually an older person or a sick person, they may have to actually have oxygen, an oxygen tank that puts oxygen into their lungs. If they have trouble breathing, you'll see them walking around with a tank on wheels sometimes, with a hose that goes into their nose, into their lungs. And it's actually putting oxygen gas into their lungs. If that oxygen gas got near a flame, it would blow up like a bomb. All right? So oxygen is flammable. The whole atmosphere would be one gigantic bomb waiting to explode if it wasn't for other gases like nitrogen mixed in to keep it under control. So nitrogen is non-combustible, it's odorless, it's tasteless, it's colorless. So this is the principal difference between nitrogen and oxygen, is that nitrogen does not combust or burn like oxygen does. All right? And then we also read there, it has a slight affinity for other substance. That means it readily unites with other substances. Okay? So that's a good idea about the properties of nitrogen. The next topic in our textbook says mineral matter in living things. Mineral matter in living things. We saw in the experiment for the detection of carbon by burning that the sand or gravel contained no carbon. If a piece of wood is burned in a very hot fire, the carbon in it will all be consumed, and eventually nothing will be left except a grayish ash. This ash is well seen after a wood fire in a fireplace or a bonfire of dry leaves. This ash consists entirely of mineral matter, which the plant has taken up from the soil, dissolved in water, and which has been stored in the wood or the leaves. So when you have that white ash that's left behind after a hot fire, if your fire is not very hot, the ash will be dirty, right? It will be blackish and dirty. So if you see black in the ash, what is that? Carbon, right? But if you get a really hot fire going, and we've had some good ones, if you get a really hot fire going, the ash will be white or light gray. And what is that ash that's left behind? It's just minerals. Okay? Just minerals. Minerals that the plants, that the tree took up into its roots and into its wood from the water in the ground. And so when we burn all the carbon away, that mineral matter that was in the tree is left behind. So where should that ash go? If you take ash out of a fireplace and it's just clean ash, where should that go?
Compost.
Yeah, back into the garden, back into the compost, right? That just goes back into the ground. So that ash is valuable. That contains mineral matter. Our textbook tells us if we were, by careful analysis, to reduce a plant and an animal to the chemical compounds of which they're formed, we should discover that both contain mineral or inorganic matter. That's what mineral matter means, inorganic matter. We have just seen examples of this in plants. Mineral matter is found in bone, in the shells covering mollusks, and in many other parts of the bodies of animals. So just because we're organic, we're living bodies, we have mineral matter in our bodies. So there is inorganic material in our organic bodies. Mineral matter. Non-organic or inorganic material. The next section is titled Water in Living Things. Water in living things. Water forms an important part of the substance of plants and animals. This can easily be proved by weighing a number of green leaves. So if you went out and collected some green leaves, some nice, bright, juicy green leaves, and brought them in and weighed them, you could get the weight of the green leaves with the water in the leaves, the way that they normally exist. If you then took those leaves and put them in the oven and heated them and dried them out, just burned all the water out of them, and then weighed them again, the difference in the weight would tell you how much water was in the green leaves. And our book asks us, how much weight of a given quantity of leaves is made up of water? If you took leaves, how much of their weight do you think would be water? And we're told, make the same experiment with some soft-bodied animals. It's pretty gross, huh? It says to do the same experiment with an animal, right? Hey, look at this nice juicy animal. Let's weigh that baby, and then we'll put it in the oven, dry it out. So it says to do that with an oyster or a jellyfish. And it says that some of these animals, like an oyster or jellyfish, can be 99% water. Their body is actually 99% water. The human body is about 60% water. So almost 2/3 of our body is just water. And if you'd like to experiment and prove that, you can just weigh yourself and then cook yourself and weigh yourself again with all the water boiled out. But anyway, the idea is that water makes up a great portion, a great part of our bodies, both for plants and animals. We'll spare any experiments. We'll take them at their word for that, okay? Maybe experiment with some plants, but we're not going to be putting any animals in the oven and weighing their cooked bodies. Okay, so we talked about mineral being present in living things, mineral matter. We talked about water being present in living things. Next, gases present in living things. Some gases are found in the bodies of plants and animals. Some gases are found in the bodies of plants and animals. Oxygen is present wherever oxidation takes place. Some plants and animals form nitrogen. Many other examples might be given. Some examples of nitrogen come from animal manure, chicken manure, cow manure. One of the reasons why it's used for fertilizer is because it contains lots of nitrogen. All right? Chicken manure contains so much nitrogen that you actually can't spread it on the garden because it's too much. It will kill the plants. You can put it in a compost pile, but you can't really put it in the garden. Where cow manure, because it has less nitrogen, it's safe to put right into the garden. Horse manure can go right into the garden. All right? So what makes the manure valuable for fertilizer is that it has nitrogen in it. You got that? What makes the manure valuable, it's not the manure itself, it's that the animals' bodies produce nitrogen. And the manure contains that nitrogen. And we can prove this because if you look out in the field, look out in the pasture where there's some manure, you'll see that the grass grows really thick and fast around that manure. And then another place, it doesn't grow so thick. We have to ask, what is it about the manure that's making the grass grow so fast? And chemists tell us that it's the nitrogen in the manure that's causing the growth. So nitrogen is a gas present in plants and animals. Oxygen is a gas present in plants and animals. The next section is titled The Classification of Organic Matter. We've got 20 minutes left, so we've got time to finish this chapter, I think. The classification of organic matter. The organic, you need to take notes. You should be taking notes. Notes help you to pay attention to the lessons. And notes also prove that you're paying attention to the lesson, but they help you pay attention. You should be taking notes. The title of this section is The Classification of Organic Matter. How are living things, how are living materials arranged in classes? How do we classify organic matter? The organic or living part of a plant or animal is made up of the elements carbon, hydrogen, oxygen, and nitrogen. The organic or living part of plants and animals is made up of 4 main elements: carbon, hydrogen, oxygen, and nitrogen. You can just remember CHON, remember CHON. Carbon, hydrogen, oxygen, nitrogen. Those are the 4 chemical elements that are the most important elements found in organic bodies, living or formerly living bodies. Carbon, hydrogen, oxygen, and nitrogen. So in the study of biology, because we're studying organic living things, these 4 elements are very important for us to know about. Carbon, hydrogen, oxygen, and nitrogen. Outside of those 4 main elements, a very minute amount of several other elements are found in organic bodies, which we call mineral matters. So carbon, hydrogen, oxygen, nitrogen, and mineral matters. Make up organic bodies. If we were to separate a plant or animal chemically into all of its various organic compounds, we would find that it is composed of various groups of tissues, the chemical compositions of which are more or less the same. For example, the living part of a plant chemically is like the living part of an animal. The actual stuff that plants and animals are made of is very similar. The starch that is found in grains or roots of plants, the starch, has nearly the same chemical formula as the animal starch found in the liver of man. The oils of a nut or a fruit are closely allied to the fat in the body of a sheep or in a cow or in a man. These building materials of a plant or animal may be placed in one of the 3 following categories. So there are 3 categories of building materials in organic living things. 3 categories of building materials in living things. 3 categories of building materials in living things, and this is obviously important. Building materials in living things. What is your body made of? What are the plants and trees outside made of? What is the actual material? The building materials of a plant or animal may be placed in one of the 3 following categories. And the 3 categories are carbohydrates, nitrogens, and fats. The first is carbohydrates, and you've seen these words before. Carbohydrates, proteins, and we'll call this 3rd category fats/oils. So these are the 3 compounds, not elements. The elements are carbon, hydrogen, oxygen, and nitrogen, right? Those are the elements. Those elements combine chemically to form compounds. The compounds our bodies are built of, and the bodies of plants, are carbohydrates, proteins, and fats and oils. And we have some description of these terms in our textbook. Carbohydrates are those materials that contain a certain proportion of carbon, hydrogen, and oxygen. Carbon, hydrogen, and oxygen. Fats and oils contain chiefly hydrogen and carbon. I'll say carbon and hydrogen. And proteins are substances which primarily contain nitrogen along with some of the other elements. Okay, but these are mainly called nitrogenous. That means high in nitrogen. Proteins are nitrogenous. Okay? So carbohydrates, proteins, fats, and oils. So you should look at these and compare them, right? What do carbohydrates have in common with fats and oils? Go ahead, tell me. What do they have in common?
They have a
Carbon and hydrogen, right? Okay, so they have that in common. What's different about carbohydrates?
It has
Oxygen, all right? What's different about proteins? Nitrogen. Okay, so we can see some similarity. We can compare and contrast them. Some similarities, some differences. Okay? Our book tells us the above three kinds of organic materials also form the organic foods of all animals and plants. All right, so not only are our bodies made of these things, but think about it. If plants and animals are made of these things, what do we eat? Plants and animals, right? So we eat the same things that our bodies are made of. We eat plants and animals. So the stuff that our bodies are made of is taken from other bodies of living things. And we do that, we call that food, right? We consume other living bodies, and our bodies break those bodies down into those compounds that our body then uses to build itself up. So it's important not only to understand what we're composed of, but it's also important for us to understand what our food is composed of. Okay, because that stuff, the material that other plants and animals are composed of is actually what we call what? Food. Okay? So the next section of this lesson deals with foods. It's 2:20. I think that I'm going to stop our class there. So we're going to cut off there just before we get to foods in this next section of our textbook. So it's going to take 3 classes to get through chapter 2. In this lesson, let's take a time to review here. In this lesson, which is part 2 of lesson 2, we finished our study of some of the basic chemical elements, right? We studied oxygen in our first lesson. In this lesson, we studied carbon and nitrogen. We didn't study hydrogen, did we? I don't think we studied hydrogen. We studied oxygen, carbon, and nitrogen. And we studied them just to see some examples of elements, chemical elements, that are important in the study of biology. Now we learned that the bodies of living things, the bodies that we study in biology, are made up of carbon, hydrogen, oxygen, nitrogen, and other minerals. And if we take those elements and combine them to form chemical compounds, the compounds that our bodies are made up of, the substances or materials that our bodies and the bodies of other animals and plants are built of, the building materials can be divided into three different kinds: carbohydrates, proteins, and fats and oils. So these are the substances our bodies are built of. These are the substances that plants are built of. These are the substances that other animals are built of. And not only are they the substances our bodies are built of, they're also the substances that our food is built of, because other plants and animals are our food. In the next class, we'll take our time to work through the remaining portion of this chapter on foods and nutrients. Okay, so take a minute in your notes, write a brief summary of what we studied in this lesson, and that's going to be all for the second part of our study of Lesson 2 in Modern Biology.